Good morning. This is your stat sensei, Mr. Spensei, and we're going to go over two sample proportions confidence intervals. Very similar to one sample, except we have two sets of proportions, and we're going to look for the difference. So when we're doing one sample, we had to define P1. Now we're going to have to define P twice for the two proportions. We're going to have to write conditions, and we're going to have to do it for both sets. And we're going to worry about simple random sample. And then we're also going to worry about, we need to make the statement the samples are independent, but we're probably going to leave that one out. So the one we're going to worry about are simple random samples. Both of them have to be simple random samples. And we have to do NP hat and N times 1 minus P hat for both. Please remember, N times P hat and N times 1 minus P hat. That is what we'll be using for the confidence intervals, and we have to do it for both of them. Our formula used to be P hat plus or minus Z star P hat times 1 minus P hat over N. Well, we got a little more complicated because now we have two, so this will be our new formula. Calculating Z star, exactly the same as we've always done. Plug our values in, run it through the calculator, write the interval, write our conclusion. Number 10 is a little bit different, and we'll deal with that when we get there. So let's go ahead and run one of these. A grocery store manager notes in a simple random sample of 85 people going through the express line that only 10 paid with checks. We have a simple random sample of 85. And this is in the express line. All right. In a simple random sample of 92 customers passing through the regular line, 37 paid with checks. Construct a 95% confidence interval for the difference in proportions for the two lines. Now, it doesn't say that, but that's what we're doing. So this is going to be very important. Oops, not P hat. Let me start that over. Let P1 equal the true population proportion of people paying by check in the express line, because that was what was first. And we always list the first one first in the express line. So order does matter. Go with the first one first. That way we are all the same. So let P1 equal the true population proportion of people paying by check in the express line. Well, guess what? That means P2 is going to be very similar. Let P2 equal the true population proportion of people paying by check in the regular line. Now, it didn't ask me to do this, but I'm going to do this anyway, and you probably should too for your own benefit. P hat 1 is going to equal to, we have it 85 out of 10, so 10 out of 85 equals 10 out of 85. And P hat 2 happens to equal out of 92, 37. Now, I realize people don't pay by checks anymore, but they used to, right? 37 out of 92. So that's P hat 1 and P hat 2. We don't have to define it there, but I want you to know what they are. This is X1 and N1, X2 and N2, right? And I'm going to go ahead and label those just so you know, X1, N1, X2, N2. And we can turn those into decimals, but we don't have to right here. All right, the next thing we get to do is we get to do the conditions. We have to do them for both. So we sit there and go, oh, simple random sample of 85. So conditions, and we're going to do conditions for P1. And we have random sample. And I'm going to just say the size, random sample of 85 given. And I'm going to expect you to do the same. Over here, I also have a condition P2. And random sample of 92 given. And I'm going to expect you to give the size, just like I did. Then we're going to have to do N1 P hat 1. So N1 P hat 1 and N times 1 minus P hat 2 has to be greater than 10. So N1 P hat, this would be N1 P hat 1 times N, that should be a 1 as well, excuse me. So in this case, we're going to have our sample size is 85, N is 85 equals 85 times 10 over 85. Well, guess what? That happens to equal 10. And this is going to be 85 times 1 minus 10 over 85. And when I solve that, I end up getting 75. This is greater than or equal to 10. And we have to make this statement okay to use the normal approx. Awesome. We're doing pretty good so far. The next thing, we have to do the same thing over here, except instead of N1 P hat 1, we're going to be N2 P hat 2 and N2 times 1 minus P hat 2. All right. Well, N2 was a sample size of 92 equals 92 times 37 over 92. Well, that's 37 equals 92 times 1 minus 37 over 92. And I'm not sure what that is. So 92 minus 37, 55 equals 55. Once again, we have to be greater than or equal to 10, which we are. So okay to use the normal approx. And yeah, I know it's not fun writing both of these down, but that's what we get to do. So it's our life. So at this point, we're ready to write our formula. And our formula is P hat 1 minus P hat 2 plus or minus Z star P hat 1 times 1 minus P hat 1 over N1 plus P hat 2 times 1 minus P hat 2 over N2. And at that point, I can go ahead and plug in. Well, what am I plugging in? Well, P hat 1 is 10 over 85. And once again, you can turn this into a decimal if you'd wanted to. So, and I think I'm going to go ahead and do that. 10 divided by 85 is 0.1176. So I'm going to write down 0.1176. 0.1176. And I also need to do the same thing for the 37 over 92. And that's 0.4021 minus 0.4021. So we've just taken care of this very first part. Plus or minus. Now I have to do the Z star. So second vars inverse norm, 1 minus, and they want us to do a 95%, so I need to make that a 95. 1 minus 0.95 divided by 2, mean is 0, standard deviation of 1. And I end up getting 1.9599. 1.9599. Now, I didn't give myself enough room, so I'm going to skip down a line because I didn't give myself enough room for all of this. I'm going to restart that 0.1176 minus 0.4021 plus or minus the z star 1.9599. Then I get to make this really long radical and put everything in there. Well, p hat 1 is 0.1176, so 0.1176 times 1 minus 0.1176. And once again, if you want to use the fraction, that's okay. And then N1, we said was 85 plus or minus 0.4021 times 1 minus 0.4021 over, in this case, 92. That's our N2. All right, next thing we need to do is we need to plug this in the calculator and get our interval. Well, this part's really easy. So stat, arrow over to the word test. We have to drop a long way down. We're going to, stat, test, we're going to drop a long way down. We're going to keep scrolling, 2 sample t interval, proportion z interval. There it is, a letter B, 2 proportion z interval. And our x1, our numerator was 10. That's what we had up here. 10 over 85. Then our x2 was 37 over 92. And I want to create a 95% confidence interval. And I press calculate, and there's my interval. Negative 0.4059 and 0.1632. And both of those are negative. So my interval is negative 0.4059 and then negative 0.1632. All right. So then we get to write our conclusion. So what are we? Well, we are 95% confident that the true population. Now, what did we do? We subtracted difference in proportions of people paying by check. Now, first off, the true population difference in proportion. Got to have that. That's the way it's going to show up of people paying by check. This just came from our definition in the, this is really important. You're not going to like it, but express line minus the regular line. Because we have to say which order we subtracted. And so I have to have this phrase, which order we subtracted. Always give me that. Lies within the interval negative 0.4059 to negative 0.1632. Now, one thing I notice is both numbers are negative. All right. And because both numbers are negative, that means, and 0 is not in the interval, that means there is a significant difference. All right. But we're not going to worry about that right now. We'll talk about that later in the week. Anyway, that takes care of this particular problem and this scenario, and I'll do one more here in a moment. All right, thank you for watching. The next one will be in the next video.